Beer's law makes it pretty obvious to us that there's a lot of power to be gained in measuring absorbance because we can actually look at a solution, literally look at a solution in fact, and determine a concentration. At least have some idea of it without being as rigorous about our measurement. Now, when we are rigorous about the measurement, how would we do it? How do we measure absorbance in order to have high quality measurements? Well, there's a couple of ways that we can do that, but let's just think through the process. And we're going to think from the end of our measurement all the way back to the beginning of what we have to do to get it. So what I want is I want to have a detector, and I want this detector to only be seeing one wavelength so that I can get a good measurement with it, right? So that means my light's got to be focused in on that detector, and it's got to be monochromatic. So how do I work it so that the light coming from my lamp, we'll give it a little filament right there. Oh, it looks really good. Yeah. Okay, so we got our light bulb, we got our light, we got our detector. What can we do in order to actually get just the color that we care about to get there and go through our sample? Well, let's do a little something to try to get just one color. So we'll go ahead and put some sort of a wavelength selector right here. Great, now I went from having lots of wavelengths to having one wavelength. Now I just need to go ahead and make sure I get that onto my detector, right? Well, no, it still has to go through a sample. So we have to have a spot to hold our sample. Then we got to get it onto that detector, right? Well, yeah, that would be one way to do it. Now, there's going to be a few things that happen, and there's a few other ways that we can set up an instrument like this, but we'll start with this one just because it's going to highlight something that we have to care about and let us see what we're actually measuring in order to find out what our absorbance is. Now, suppose we had an instrument set up kind of like this. The first thing we'd probably do is we'd go ahead and we'd put some water into our sample, right? And if we put in water, or whatever our solvent is going to be. So it's everything that we have that we need except for my actual sample molecules. We're going to have that sitting in the cuvette. So it's solvent and cuvette and probably some dirt and everything else, in other words, except for my sample. We're going to do a measurement of that stuff. And we're going to look at how much intensity I'm seeing from that light. So the detector looks back and says, aha, I'm at some power. We'll call that P naught. That's my original power that I had. Now I'm going to swap my real sample in there, and it's going to be the same thing except that it's going to have my sample in it. In other words, it's the same solvent, it's the same cuvette, or at least a very similar cuvette. You know, hopefully we didn't have any fingerprints on the cuvette, so hopefully this term didn't exist in the first place. But if it did, and we have the same cuvette with the same fingerprint arranged in exactly the same way, that shouldn't throw off our measurement, right? We do all of that, but now we have my sample. That's going to be a different amount of power, and it's going to be a smaller power. So what if we didn't do the same measurement? What if we had done it for just no sample cuvette sitting there as my original power? Well, that would have been off, right? We weren't accounting for the absorbance of the sample holder, the cuvette, and all that other stuff. So what we need to actually consider is going to be some sort of a ratio between these two. That's going to be the thing that actually tells me something meaningful. So the light that actually makes it to my detector is going to be the light that's transmitted. And so I can say, well, if I want to know the transmittance, I can say that the power that I'm actually measuring divided by my original power, that should be my transmittance. Now, that's all well and good, but that's just going to be some decimal fraction. More usefully, we often like to make that into percent transmittance because that's something that is really readily apparent to our mind. Because then we can say instead of 0.5, 50% of light was transmitted. Now if we do that, then it's going to be P over P naught times 100%. Just make sure that you're being very careful to distinguish between T and percent T whenever you plug these into equations later. You always want to make sure that you know which one you're dealing with, and it's pretty obvious because if you're doing it right, you're not putting a percentage after this number, and you are putting a percentage after this number. And, once you've got one, it's just a matter of shifting the decimal in order to get the other. Great, so we're talking about transmittance. But in the other videos, weren't we talking about absorbance? We need to get from how much light got transmitted through my sample into that nice absorbance unit that's actually going to have a linear relationship with my concentration, right? Now, for that to happen, what we need to do is we need to take the negative log of transmittance. So negative log of transmittance, notice not percent t, that will equal absorbance. This is one of our important relationships to remember. Now that also means that we could think of that as being log of initial power over our current power. Or we think that is negative log, and we'd have these two inverted. And if you remember back to what we've done with log, and all the way back when we were talking about equilibrium constants, you probably saw that, when you flip it, you just end up changing the sign. Be very careful not to mess that up on here too. The key thing is to remember that when you've got a transmittance that's between a percent transmittance that's between 0 and 100%, then your absorbance better be a value, like a positive number. It can't be a negative number, right? So that's how we would do an absorbance measurement very crudely. Now that said, is this what a spectrometer always looks like? And the answer to that is going to be no. Resoundingly no. So what we'll take a look at later in this chapter is exactly what we can do to this instrument to make it do more things for us. And we'll also be talking about the individual pieces of hardware as you go through the entire spectrometer.